Now I realize that some of you have done this before, but given the complaints that I've had from other instructors in econometrics that students are not always well prepared, I decided that this is one of the things I want to do. All right, let's start with a matrix A, which is given by, or we write it like this, with A 1, 1, with the 1, 1 denoting the first row in the first column. And we can put up other elements. And let's put A1, 4, which refers to the fourth element in the first row. So let's just erase this comma as it's not needed. And let's then say that we have 4 rows in this matrix and 4 columns. And we can denote that, and we write it like that. We can denote that simply as a matrix that looks like this, where you have element A, I, J. The I refers to row, the J refers to column. And this is then a 4 by 4 matrix. Now, more generally, we can write a matrix like this. So let's write matrix B, and let's assume that matrix B is going to have Q rows. So A1, 1 down to AQ1, and let's say that it has P columns. So then we basically write the same kind of thing, but we now denote this somewhat differently. And this is a Q by P matrix. And again, we can write this as AIJ, but this time it's Q by P. All right, so let's add another sheet there. And what we do is, if P equals Q, this implies that we have a square matrix. So matrix A, for example, was square because it was 4 by 4. Now, a diagonal matrix has zeros in the off-diagonal elements. So let's say D is a diagonal matrix where we have D 1, 1, and over on this end we have D K K. So in other words, we have a K by K matrix, and we have zeros on all the off-diagonal elements. So D can be written as a diagonal matrix like this, D1 all the way to DK. Okay, yeah. All right, so a lower triangular matrix we can define as follows. Triangular matrix. Now we have to be a little bit careful here how we set that up. Let's denote it with an L, and let's say it's going to be QQ, Q by Q, which means it's a square matrix, and lower triangular matrices have to be squared. So what we do is we write A11, A22, A33, all the way down to AQQ, and we get A21 dot 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 AQ1. Here we have A3, 2, and so on down to AQ2, and then across to there, and this is a Q by Q matrix, and there's 0 on all the elements beyond that. So these are all 0. Above there, there's a 0, and so on. Okay, likewise, we have an upper triangular matrix, which is exactly the opposite. All right, except that it too has a section, a triangle that's denoted by zeros. So again, we go A, 2, 2, all the way to A, Q, Q, and we have A, 2, 1, pardon me, I have that wrong. This should not be A, 2, 1, this should be A, 1, 2, and this is A, Q, 1, 2. We have A, 2, 2, A, 2, 3, all the way out to A, 2, Q, and so on down. And all of these are zeros on that side. And again, it's a Q by Q square matrix. Okay, so, and we define Aij is equal to 0 for all, and that little thing there means for all. And we can define Aij for all I less than j. And we can define Aij is not equal to 0 for all I greater than or equal to j. Okay, so if that's for an upper triangular matrix. And let me just be clear about this, that this is for I greater than or equal to j. And likewise, for a lower triangular matrix, we can write that exactly the opposite. Again, Aij is equal to 0 for all I greater than j, and Aij is not equal to 0 for all I less than or equal to j, and that's a lower triangular matrix. Okay, going back and looking at what this here means, all right, we also denote this, let me just make that a little bit clearer. We denote that element refers to such that, and this one you're familiar with is an element of. So this is the kind of notation that we use. We also can talk about a transpose of a matrix of A, matrix A, we write as A to the T, or sometimes simply A prime. So matrix multiplication. So let's take those two matrices that we had, 5, 6, 9, and 4, 3, 2, and we multiply them by the matrix. So this is a 2 by 3, and this one is 5, 6, 9, 4, 3, 2, and when we multiply those, this is a 3 by 2. So we should get, all right, when we eliminate those, they have to be equal, 3 and 3, we'll get a 2 by 2 matrix. So we can put 2 by 2, and we multiply the first row, we'll multiply the first row, this one here, with this column. And that will give us the first element. If we do that, we get 5 times 5 is 25, plus 36 is equal to 61, plus 9 times 9 is 81, plus 61 is 142. Then the second element is when we multiply that first row by the second column. So we get 5 times 4 is 20, plus 18 plus 18. 18 and 18 is 36, plus 20 is 56. So that gives us this element here. Then we multiply this second row by each of these columns. So we get 4 times 5 is 20, plus 18, plus 18 again, and that gives us 56 again. And now we multiply 4 times 4 is 16, plus 9 plus 4. So that's 29. And this is a 2 by 2 matrix, and we'll denote that. Let's just call it R. Okay? Now, can we add these matrices? Can we add the two matrices? And the answer, of course, is no. Why? Because the dimensions are not identical. They have to be identical if you're going to multiply or add, rather, two matrices together. So 2 by 3 versus 3 by 2 cannot add. If we have 2 by 3 versus 2 by 3, can add. So we can add them together in that particular case. All right. So when we multiply A times that, we get what we had before, R. But suppose we do A times 2. Then what we had was AT was a 3 by 2 times A, which was a 2 by 3. So now we get a matrix that's got to be 3 by 3. And it's a matter of filling in how that works. All right, and if we do that, we start with, well, let's put that out. Okay, so we get 5, 4, 6, 3, 9, 2. All right, that's our transpose. And we get here 5, 6, 9, 4, 3, 2. All right, so this one is 2 by 3. 3 by 3 by 2, and this one is 2 by 3. So if we fill that in, and we'll do that up here, we first get 5 times 5 is 25, plus 16 is 41. Then we get 5 times 6 is 30, plus 4 times 3 is 12, plus 30 is 42. Then we multiply 5 times 9, which is 45, plus 4 times 2 is 8, is 53. And we continue to do this. 6 times 5 is 30, 3 times 4 is 12. We get 42. Again, same as we had on the other, when you compare those two, same. Then we multiply 6 times 6 is 36. 3 times 3 is 9, 36 and 9 is 45. Then we multiply that 6 by 9, and then that gives us 54. 3 times 2 is 6, and we get 60. And we can continue doing that, and we end up with 53 here, 60 here, and 109. And not surprisingly, this is a symmetric matrix. Why? Because the elements in the off diagonal, so because Aij is equal to Aji. All right, that's the definition of a symmetric matrix, or more formally, if A is symmetric, so if A is a symmetric matrix, that implies that A transpose is equal to A. Okay? Now, what is A plus B is equal to what? Well, you can only add them, so we're getting back to the if and only if number of rows or columns of A equal number of rows and columns of B. So if A is equal to 5, 6, 9 again, 4, 3, 2, so it's a 2 by 3, and B is equal to, say, 4, 0, 3, 12, 8, 1, which is also 2 by 3, then A plus B is equal to 4 and 5 is 9, 6 and 0 is 6, 9 and 3 is 12, 12 and 4 is 16, 8 and 3 is 11, and 1 and 2 is 3. And that's a 2 by 3 matrix. Now, what about equality? When are two matrices equal? A is equal to B if and only if Aij equals Bij for all I and j. All right. So then we have some kind of transitivity, not transitivity, but we have this rule here that it doesn't matter if A plus B, whether we add A to B or B to A. All right. And we can go a step further here. All right. If A plus B plus C is equal to A plus B plus C. So we can change the order like this. So we can add first A to B, or B to A rather, and then add C, or we can start with A, we can start with B plus C and then add A, or vice versa. We can also define C as a vector 0 or a matrix 0 as follows. P by Q. So we have a P by Q matrix of zeros. All right, and that arrow on top of the 0 here is indicating that it's a vector, or I usually like to use an arrow. Arrow often designates vector. Okay, so if an arrow is above a number, it usually indicates a vector of whatever the number is. So if I have a 6 with an arrow over it, and then I'd have to give it dimensions of some sort. All right, and usually a vector will be 1 times p, let's say, or p by 1. If it's 1 by p, it's a row vector. So that's a row vector of 6s. And we can have, if we have 0, then we can put immediately here p by 1, which means it's a column vector. So that's a column vector. So that's why I don't like to use that. So I really should take that bracket off that 6 and just put 1. Should just put, so 6 with an arrow above it is 1 by p. All right, then it's a row vector of 6s. Okay, what are some other things that we have? We have A plus C is equal to C plus A is equal to A if C equals 0. Again, let's just go and just do and put that above. And then we would assume the same dimensions for 0 as A, of course, because otherwise we would not have the ability to add the two together. Okay, what about scalar multiplication? So scalar multiplication is where we multiply all of the elements in a matrix to multiplication. So let R and S be scalars, and we multiply S, A, M by N. So in a matrix A, that's M by N, is equal to S, A, 1, 1, all the way across to S, A, 1, N, and then down to S, A, M, 1, and then over to S, A, M, N. So what we've done here is we've multiplied each of the elements, each element multiplied by scalar S. So we could also write that as S, A, M by N is equal to S times A, I, J, M by N is equal to S, A, I, J, M by N. All right, that's scalar multiplication. Now, suppose A is equal to 2 and 4. So it's a row vector, and B is another row vector with elements 4 and 1. And, oh, we don't want that yet. So we're going to stop the recording at this point and move to a new page. So if the scalar fs is equal to -1, then A plus -1 times A is equal to 0. All right, whatever the size of A is, if A is M by N, then this is M by N as well. So A plus A we can say is 2a. So if we have that r plus s, a is equal to ra plus sa. So you can split up the scalars that you're multiplying a by. So then we have r sa is equal to s ra if we break them down. Okay, vectors. We've already talked about vectors to some extent, but we usually denote them as v1 ... vn. So this is a row vector that's 1 by n. All right, v prime or v transpose is then equal to v1 ... vn. All right, and it's n by 1. And let's just call that one u. All right, then v times, where v is, let me just make that a little bit clearer. V is a 1 by n vector times u from the previous whiteboard is n by 1, and that gives us a scalar, which is 1 by 1. So it's equal to v1 u1 plus v2 u2 plus ... vn un. Now we can also go v prime n by 1 times u prime 1 by n. Now we're going to get something, because remember that 1 is going to cancel that 1. So we're going to end up with something that's n by n matrix, and that's equal to v1 u1, v1 u2, and so on, v2 u1, v2 u2, and so on, and all the way down. And that's going to give us this n by n matrix. All right, so you've seen much of this before. So now we're going to look at vectors in terms of diagrams. So I'm going to do a fresh page here. All right, let's let A be a vector 2, 4, and B be a vector 4, 1. Now, why is this of interest? Well, let's just draw a Cartesian plane, and we'll see how good my hand drawing is here. So we have 1, 2, 3, 4, 5, and let's go to 6, and the same thing here. 1, 2, 3, 4, and let's go to 5 here, and put some, and that's our 0. So we have a vector E1, we'll call it. So 1, 2, 3, 4, and this vector here, all right, remember it's a directional vector, so we'll call that one E1. And the same thing, all of these vectors along the horizontal or vertical axes are a directional vector. But here what we have is we have this vector A, and let's just put a, I don't know why the line above it to show that they're directional vectors. So A is going to go out by 2, so it's going to go, I'm just going to change to a red color for A. It's going to go to here and to 4. So we'll go up to 0.4 here. So this is the terminus of vector A. So we can put vector A like this. Okay, there we go, and that's the direction of vector A. just highlight that a little bit, make it a little thicker so it's a little clearer. And then let's use a blue to look at vector B. Vector B goes out for 1. Come on, stay steady here. Goes to here, and then it goes to 1. So we can just look at it here, and it's point right there. So this one looks like that. Okay, so again, we'll put a head on it to indicate where it goes, and we'll just thicken that a little bit to make it a little clearer. All right, there you've got 3 vectors. You've got B here, and you've got A here, and we're going to add these 2 up. All right, and the sum of these is what? Plus B is equal to 6 and 5. Okay, so that means we're going out here to 6 and to 5. So that brings us all the way out here to 6 and 5. So this is where the sum of these 2 matrices goes. All right, let's thicken that line just a little bit to make it a little clearer. All right, so this is the sum of A plus B. A plus B. All right, now what we've done is we've taken this blue vector and we're basically adding it in this fashion here to the A one. So that dotted line should be the same as this blue line. And likewise, we're going to take the A vector and we're going to add it to this one. So here we have that A ending and the blue one here. So that's how we get that point there. All right, so we've added the 2 up, and this is where we end up with the 2 of them, A plus B. All right, let's go and look at a bit more here. Okay, so the length of A, so the length of a vector A is equal to A bar, we'll say. Length of vector A equals, we'll denote it with A bar, and it's equal to, remember it was vector 2 and a 4, so it's 2 squared plus 4 squared, and the square root of that, which is the square root of 20, which is equal to 4.4721. And the length of B is square root of 4 squared plus 1 squared, which is equal to the square root of 17, or 4.123. Okay? So the distance of A, or the length, is equal to 2 over square root 20 and 4 over square root 20. Okay, so this is not the length of the vector. This is the, if you like, the normalized vector. So think of it as that this E1 vector, because E1 looks like this. E1 is equal to 1, 0. Okay? And we can have E2, which is 0, 1. So we can have that vector here, which is E2, is 0, 1. So these are directional vectors, and we want to make A into a directional vector by shrinking it. Okay, shrink to normalize it. So it'll have to be somewhere in here. Okay, so this would be A, and we'll denote that by AD. All right, so here we have AD, which is equal to 0.4472 and 0.8944. So this point here on the length of that vector has to be, I've got it way too long, and it should really be, let me just grab the red one, it should be somewhere around here. All right, so this would be the length of that vector A. All right, because it has all right, the first number should be about 0.45. All right, and that would be about here somewhere, 0.45, and the other one is 0.89, so it should be a little bit higher, so it should be somewhere in here, but it's got a touch. So somewhere there is where we get the normalized vector A. All right, now let's look at this AD a bit more. So if we look at the length of AD, we find that it's equal to 0.4472 squared plus 0.8944 squared, and then the square root of all of that, and that's equal to the square root of 1, which is equal to 1. So the vector has length 1. So we can define E1 as, remember in the where I just had a two-dimensional coordinate system, where I had a two-dimensional coordinate system, I had the vector 1, 0, but now in a three-dimensional coordinate system, E1 would look like this. E2 would look like this. And E3, the third dimension, would look like that. All right, so those are our normalized vectors. Okay, so we add another page here, then what we'll do is we'll look at, again, I'm going to build a coordinate system, and those same two vectors that I had on it, all right, so I had this vector B, which looked something like that, or pardon me, this was A, and this was vector B, something like that. And what I want to do is spin that around. I want to change the coordinate system, all right? So this becomes a linear combination. So we want to create a linear combination of A and B, of the vectors A and B, all right? Why would we want to do that? Well, there are a variety of different reasons, but one of them is used in statistics, okay, multivariate analysis. And let me show you what I mean with an example. Suppose we have something that looks like that. We have all kinds of data, all right? And let's say we have, this is our x1, this is our x2. And we want to look at observations. Suppose we had observations all along here. All right, so basically we have zeros, 0, 0. Okay, these are different kinds of observations. All right, of some particular kind of, let's say they're observations on wing size of birds or something like that. And what you can see immediately is that you can draw a line through this, all right, that basically separates the observations according to a specific element that's not truly represented by x1 and x2. All right, there's something else at play here. All right, there's something else at play. So what we want to basically do is we want to rotate the axes this way. All right, so that this becomes y1, and then we have, to keep it orthogonal, we have a y2, okay, which is here. So basically we're taking the red system and we're rotating, or we're taking the coordinates x1 and x2 and we're rotating that whole graph until the x1 is the same as the y1 and the x2 as the y2. So we get a linear combination of x1 and x2, which looks like ax1 plus bx2. And we just have to find what A1, or pardon me, A and B are going to be. All right, so let's go back and think about this. Happens here. Oh, how do we look at these directional vectors? So remember, A is equal to 4 and 3, and we can look at half of A and we can plot both of those. All right, is equal to 2 and 3/2, and we can add two vectors, 2, 2 plus 4, 3, which is our A. Okay, and we can call this one B, let's say. So that's B, and this is equal to 6, 5. So if we were to plot this, okay, we plot this like this here. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. This is not to scale by any means. 2, 3, 4, 5, and I want a 6 here. So the 1, A is equal to 2, 4, 3. So we get 4 and 3. So let's draw that with red. So that again is A, and this is minus A. So this would be minus 6 and minus 3. Pardon me, this would be minus 3, and this would be minus, this would be minus 3, this would be minus, this would be minus 4, right? So that's minus A, and this is A. And then we can have our blue one, which is, I'm going to use that 6 and 5. So we go up here, and 6 and 5. So we have that one just coming like that. All right, so this is 6, 5 directional. All right, so this is A equals 4, 3. I want the red one. 4, 3, and 6 and 5. And we can also add the B vector, which was 2, 2, which is somewhere in here like that. Anyway, you get the drift of how we put together how we find the directions, how we find vectors in Cartesian space. Okay, that'll end this particular lecture, and I'll go on to look at how you solve a system of equations using matrices in the next lecture.